Hey guys, welcome. Yeah, so I hope you're doing well. And now, in previous years, I've already made solutions for the 2019 FRQ full length solutions. And I also have further in the past made solutions for the 2018 FRQ and yada yada. So, why this video? Well, because of Corona, we know that the AP is going to be quite different this year. First, it's going to be done at home. Second, lots of topics are trimmed. And third, it's only 2 questions. Now, I'm going to make a prediction. Come back and thank me later. My prediction is that one of the 2 questions, for sure, will be on Taylor McLaurin series. Why? Well, first of all, Taylor McLaurin series is one of the topics that they have kept, and it's really like the punchline to Calc BC, right? Like it's what you learn towards the end, and it's arguably the most important idea and the coolest idea also. So they're definitely going to have a Taylor McLaurin series. So I'm betting my last dollar that one of the 2 questions on this year's FRQ is going to be a Taylor or McLaurin series. Now, we know that McLaurin series is just a Taylor series centered at 0. In fact, as I'll share in the questions that you will see, in some questions they'll just say the Taylor series centered at x equals 0 instead of calling it a McLaurin series. But you should know that McLaurin series is just a Taylor series centered at 0. Okay, so what will you find in this video? Well, I guess it's kind of their tradition. In previous years, the Taylor McLaurin series question has always been the last. It's been the 6th problem on the 2019, 2018, 2017, and the 2016 FRQs. You can look at the full FRQ tests and fact check me. So I suppose it's a tradition, but it's been there every single time. In fact, one of the 6 questions will frequently be substituted for one topic and another, right? Like, in other words, like sometimes like they'll have a parametric equation FRQ instead of a polar, right? But what's always a mainstay, right? What's always present is a Taylor McLaurin series question. So, word to the wise, watch this video. That's why I have dedicated my FRQs in preparation for the 2020 BC test being entirely about Taylor McLaurin. I'm not going to share another video. This is it. Because, again, I will bet my last dollar on this. All right, so where do we begin? Well, we're going to begin with the 2019 FRQ problem 6, which is the Taylor McLaurin series question. And then we're going to look at the 2018 here in this video, that is. And then we're going to look at the 2017 and then the 2016. And finally, there was a kind of like AP style. It's not kind of, it is an AP style question, again, about Taylor McLaurin series, but it's one that a student that I was tutoring shared. And it's a question that will present you challenges that are not in any of these 4 FRQs. And so it's kind of an interesting one that you ought to learn. That's going to be the last of them. So basically, I'm going over 5 questions that are all about Taylor McLaurin. Finally, before we begin, read Part D. Again, as if it's tradition, like Part D and the 2019, 2018, and 2017 yada yada FRQs has always been about the alternating series truncation error. That is the alternating series error bound. It's also known as that. And what's happened this year is that they're not going to ask you about it because, well, they've already said it's not going to be on the test. That means that we could get rid of this Part D, which is awesome because, well, we need space. All right, so you can go ahead and read this. I'm not going to read it out loud, but I'm going to begin the solutions. Let's begin with Part A. Of course, you need to know the Taylor series formula. And we know that the Taylor series formula, you need to have this memorized. Yes. I've been told by students that it's an open book test this year. And so then open notes, so you can use resources, whatever you want. And you can even use calculators. But these people are smart. So first of all, you're timed. So the more you memorize these like important things that you've had to memorize in the past, the better off you'll be, right? Like You'll save time because it's a timed test. Second is these people are really smart people, so they're going to design a test that you can't cheat on, where the calculator is not terribly helpful. And if you don't know what you're doing, in other words, you don't master these topics, then you're not going to do well. They're going to create it, design it that way. There are a bunch of like gimmick videos where they talk about like, oh, cheating is possible in this FRQ. No, like these people are smarter than these idiots that are making YouTube videos about cheating. It's not going to happen. Watch. And also watch. This idea will be on the test. Okay, let's get started. Enough said. So we know that the Taylor series generally is defined as this, right? And then it's x minus a to the power n, right? And of course, when a is equal to 0, that is the center of the Taylor series, a is equal to 0, we get the maclaurin series. And so we know that the max series is going to be like, I guess I'll write it in red. I was tempted to write it in a different color. It's going to be n equals 0 to infinity, fn of 0 over n factorial, and then x to the n, right? This is when a is equal to 0, right? Okay, now, I assume that you've been paying attention in your calculus class. So while I intend to break down my solution for every problem, I can only like break it down so much. Like I can't teach you arithmetic, for example. So I can't teach you like, some details that I assume you should know. Part A says, write the third degree Taylor polynomial for f about x equals 0. Okay, so they're talking about the maclaurin series. So we're actually using specifically this formula on the right-hand side. Now, since it's saying third degree, right, it would be useful if we wrote this sigma expression term by term. This sigma expression is called the closed form because, well, it's like a closed form. I don't know how to explain that. But if we write it term by term, this here is saying this. It's saying that f of x is equal to, as an infinite polynomial, when n is equal to 0, we're going to get f0 of 0. First, let me explain before we proceed again, although you should know this is saying the nth derivative evaluated at 0. So when n is equal to 0, we're saying the 0th derivative. Well, that's before you took any derivatives, so that's the function's value. So that's just f of 0. Yeah, okay, so we go f of 0. And then, yes, 0 factorial is 1, x to the 0 is 1, and so then we don't need to write like this item or this item when n is equal to 0, so we keep it moving. So we go f prime of 0, and then it's x to the first, so I'll just write x, and then over 1 factorial, right? And then plus f double prime of 0, and then it's x squared over 2 factorial. And we need the third degree, so we need one more term. So plus f triple prime of 0, and then x to the third over 3 factorial. Now, a quick note on like why they use this kind of like weird notation that you're not taught in class. Well, you are taught it, but like that's not discussed heavily in class, right? When we talk about derivatives, we don't really write it like that. The reason why we do that is because like these like tick marks, they get cumbersome, right? Like what about you talking about the 10th derivative? Well, it's better to write it like this, right? That's why. Just a quick side note for kids who need that. Most of y'all don't need it, but it don't hurt. It don't hurt. Sorry, hold on. Let me use lasso instead of a rectangular one. Okay, so clearly they're smart. They've designed the question so that you can find f of 0, you can find this, you can find this, and this. And those are all the things that you need to find. Everything else is, good as it is, right? Okay, so they gave you a combination of a graph and tables for you to find out these things. So for f of 0 and f prime of 0, we use the graph given. And then for these two guys, we use the table given. Now, f of 0 is the function's value at 0. Now, they intentionally made this curve, which is supposed to be a part of f, not quadratic. Look at it. It's not symmetric. It's not quite quadratic. So you know that like it's some weird function that's going to go on that you have no idea what it looks like. But you're given a portion of it. And so then at 0, f of 0 is 3. So that means this item right here is 3. Actually, I want to write in black. Black and yellow. Just kidding. It's black and red. Okay, so 3 plus f prime of 0. What is that? If you were paying attention, they said that at x equals 0, this is a tangent line. So we know that f prime of 0 here is the slope of the tangent line at x equals 0, right? Because this tangent is tangent at x equals 0. And so then we're going to find f prime of 0 by counting the slope of the tangent line. And for that, perhaps we should switch to blue. All you got to do is pick two lattice points. Lattice points are points with integer coordinates. And so you could go up 1 to the left, sorry, up 2 to the left 1. So up 2 to the left 1. So that's 2 over -1 or -2. If you didn't see that this was a lattice point, you could have used the one over here. Same thing. This time, though, it's going to be up 4 and to the left 2. That's still -2. So f prime of 0 we see is -2. Okay, so we're going to write -2 and then x, right? And that's probably best written as, let me do this, sorry, -2x, right? And then plus, otherwise, f double prime, that's when n is equal to 2, right? Because remember, what we have said is that this here is saying the nth derivative. So when n is 2, it's saying the second derivative. So this here is the same as f double prime of 0 in context. So that's clearly 3 from the table. So then what we've got is we've got 3 over 2 factorial and then x squared. And then next is f triple prime, right? And so that's right there, but don't forget, so it's negative, so then let me get rid of that. Don't forget that we have to divide by 3 factorial, but that's 6. So the 6 is going to multiply that 2, so it's really a 12. So I'll just write a 12 here, x cubed. And if you do this, then you get full marks for part A. Yeah, okay, cool. Now, I apologize that there was quite a lot of setup conversation, but we're going to stay focused and get these done as efficiently as possible. Okay, in part B it says, write the first 3 non-zero terms of the Maclaurin series for e to the x. E to the x is the second simplest Maclaurin series, and it's sweet, beautiful, nice and simple, and it's n equals 0 to infinity, and then it's x to the n over n factorial. So based on this, the first 3 terms are going to be 1, and then plus x, and then plus x squared, right? And of course we could go on, but we only need the first 3 terms. Okay, again, some students, when I've worked with them, have said, well, it's open note, blah, blah, blah. Who cares? Just know it. I already made the point that it will help you do it efficiently, right? So we take the first 3 terms of e to the x, which I just said is 1, and then plus x, and then plus x squared. And we also know the Maclaurin series for f of x. And it's nice that they interchanged between Taylor series centered at x equals 0 and the Maclaurin series. I guess they're trying to see that that lingo, that Taylor series centered at x equals 0 is the same as Maclaurin series. But anyway, we have the Maclaurin series for f of x, and so they're having us figure out the Maclaurin series for e to the x times f of x. Well, we already wrote down e to the x, and then for f of x we can use this, right, what I have in black, and I guess just to make sure that we see it, and let me go over f in black. I could write 3 minus 2x, and then plus 3 over 2 factorial, and then x squared, but I'm going to stop there, and I'll explain why. Because they're asking us for the Maclaurin series for this function, and it's the second degree that they want. Right, and so already we have more than we need of e to the x and f of x, because you'll see what we have to do to find the Maclaurin series for the product of e to the x and f of x is multiply these two, which amounts to foiling. But when we foil, look at what's going to happen. Well, I'll do it in blue. First, we multiply. That's not blue. Hold on. First, we do this, right? That's 3. Okay, and then next we do this, right? And that's minus 2x. My handwriting is really sloppy today, but I'll live. And then next is that. And so that's going to be plus 3 over 2 factorial and then x squared, right? And after that, we go on to this here. That's 3x. So plus 3x. And after that, we go there. That's minus 2x squared. And if we go any more, notice that this is going to give me an x cubed. I don't need that because they said the second degree. So that's what I was talking about. We already had more than what we need. And I suppose, so you can see what we have to finally do. I'll do it in a different color. No, I'll stick to blue. So then next, what we have to do is distribute the x squared, right? So when we do that, we get 3x squared. But then if we send the x squared over here, we get an x cubed term. Again, that's more than our requirement. And so all you have to do now is a little bit of simplifying. Specifically, this minus 2x and that 3x will turn into an x. And then, of course, you have this, and then this and this making up the x squared term for the second degree Taylor. I'm not much into simplifying and arithmetic and such, and so I'll leave that work to you. Okay. It looks like I can only backtrack so much, and that's, I love this tool, but it's got a few handicaps, and that's one of them. Why can I not just like hit backspace ad infinitum if I want? Anyway, part C, we can read it. It says, let h be the function defined by, so h is the integral of f from 0 to x. All right, so h of x is the integral of f from 0 to x, and for reasons that have to do with like proper integral grammar, this inner variable had to be different from this upper limit, right? That's why they use t. But for f of x, whether we use f of t or f of x, is still the same function, right? And I don't know if your memory is as good as mine, but you see f of t, which I had erased, well, we have it here. But I could do it off memory. Look. Just real quick. Yeah, keep you engaged. So I suppose I might as well make it interesting also, right? So it was 3, and then it was minus 2x, and then it was plus 3 over 2 factorial, and then it was x squared, and then it was minus 23 over 12 x cubed, right? Okay, so, well, my only flaw, I hate flaws. My only problem in this design is it's not x, it's supposed to be t, right? Because inside it's supposed to be that. All right, sorry guys, a little bit more time than I wanted to spend on this, but we're good. It was like literally like 4 seconds longer. I was counting. Okay, then dt, right? Okay, cool. So then we see that h of x is going to equal 3t, this here is the integral of that, and then minus 2t squared over 2, right? And then which is just minus t squared, right? So let's just write minus t squared. Why not simplify as we go along? And I'm going to do this casually, but I'm going to try to do it efficiently also. And the next one is going to be plus, and then it's going to be t cubed over 2 factorial, because, well, it's 3t cubed over 2 factorial divided by 3, but then that reduces to just this, right? Okay, I said casual, but I didn't say slow. So minus 23t to the 4th over 48, right? And then, of course, all we have to do is plug in x in this and plug in 0 and take the difference. Notice that when we plug in 0, since all of them have t's, it's going to annihilate every term. In other words, they're all going to turn into 0. So all we're going to get is like what we already wrote down with x's in it. So this is going to be 3x, and no wonder, because h is a function of x. 3x minus x squared, and then plus x cubed over 2 factorial. And then, what is it? Minus 23. It's not 23. Minus 23x to the 4th over 48. And they said find an approximation of h of 1. Well, so you just plug in 1 into this and whatever number that is. Again, I'm not going to do the number crunching. But I do have an interesting point to make here, which is, why is it that they're saying find an approximation of h of 1? Because if this is h of x, why is plugging 1 in here an approximation of h of 1? Well, because we only used so many terms of the series for f. And so when we integrate that to get h, well, if h is the integral of f, since this is not all of f, this is not all of h. and therefore this here is an approximation of h, right? It's a fourth degree approximation of h, right? Okay, so I thought that was like kind of a subtle lice. That's on my head. No, I'm speaking too fast now. I slow down. No, so I thought that was a nice little subtle note to kind of talk about, but we're done here. So let's move on to the next one, right? And so this here, as you can read, is from the 2018. And so what is this about? I didn't prepare these ahead of time, so we'll have to read together. So the maclaurin series for ln of 1 plus x, yeah, we love it. It's there. And on its interval of convergence, this series converges to ln of 1 plus x. Wait, what? Isn't this redundant? Okay, let f be the function defined by this. Got it. Write the first four non-zero terms in the general term for the maclaurin series of f. Got it. So we see that first we should work on this. This is just modifying this, right? How are we modifying it? Well, in place of this x, we have to put an x over 3, meaning that then we have to put an x over 3 everywhere we see an x, here, and here, and also in the general term, right? So what I'm saying is, to start, we see that if I may write in black, we see, and I'll write up here, we see that ln of 1 plus x over 3 is going to look like, this is going to look like x over 3 and then minus x over 3 squared over 2 and then plus x over 3 cubed over 3, right? Okay, and then minus x over 3 to the fourth over 4. And how much of it do we need? The first four non-zero terms. And they keep saying non-zero terms. Why? Because, well, there are maclaurin series like sine and cosine that have terms missing. Like for sine, we know that the even exponents are missing. And so if for sine, they said the first four non-zero terms, or let's keep it to like the first three non-zero terms, then we'd have to go all the way to x to the fifth. So that's why they're saying that. Yeah, okay, just a side note. But anyway, we're done getting to this part, right? I mean, we have a little bit of simplifying work to do, but we also need the general term, right? Okay, and we'll get there. So the general term then is plus dot 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 first for this. Getting to f is pretty easy. All we have to do is multiply this by x, right? So dot 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 and then plus. Again, really sorry about my handwriting, but normally it's really, really neat. Yeah, blow my own horn. Why not? Okay, and x over 3 to the n over n, right? Do I have that right? Yes, and then plus dot dot dot. Okay. And of course, the only thing we need now is this x, and if we have that, we have f of x, right? So I'll be like f of x equals, well, we just need to throw an x there, meaning that we multiply all of this by x, right? Okay, so when we do, we're going to see that f of x, I suppose I could write it here, f of x is going to equal, and we can simplify simultaneously. See, I knew what was coming, over 3. And then it's going to be minus what? Well, from this part, it's going to be x squared, but then we're multiplying by this x, so it's going to be x cubed. So minus x cubed, and then over 3 squared times 2. And I'm writing it as 3 squared times 2, even though I know arithmetic. I know that's 18, because, well, it might help us figure out what the general term is. Not in this particular problem, because, well, we already are working on getting the general term. But in other places, you know, if you're trying to figure out what the general term is based on the first so many terms, it will be useful if you don't, like, change this into an 18, because it will mask what's going on. Yeah, so that's great advice. Take it. And then it's plus x to the fourth over 3 cubed, and then times 3, right? Okay. And then minus, and again, it's x to the fourth and not x cubed, because we've got that x right there. And then it's going to be minus x to the fifth over 3 to the fourth times 4. And then it's going to be plus dot dot dot, and then plus negative 1 to the n plus 1, and then it's x to the n over, no, not x to the n. I almost rushed because we're still multiplying by that x, right? So it's x to the n plus 1, and then over 3 to the n, and then times n, of course. All right, so we have just successfully finished all of part A. Determine the interval of convergence of the maclaurin series for f. Show all the work that leads to this. Really, do we have to? Yes, we do. So interval of convergence is always answered through the ratio test, right? And so then that's what we have to do. We have to do the ratio test. And so first, let's write f in closed form. So we see that f of x in closed form is equal to, this is not much work. It's n equals 0 to infinity, and then just throw in the general term, which is negative 1 to the n, and then x to the n plus 1, and then over 3 to the n times n, right? This is the general term. Got it. Now, just as a quick, extra check, plug in n equals 0 to see if you get the first term appropriately. And do we? If we plug in n equals 0, we do not get the first term, right? So then that means that we did something wrong. No, it doesn't. It means that this needs to be n equals 1. See? That extra cautionary stop was really useful. Now we do get this when n is equal to 1, right? Yeah, so we're good. And in any case, the reason why this was not n equals 0 is because the maclaurin series for this doesn't start at n equals 0, right? Okay, so that's that. All right, anyway, here we are. And so then, we didn't really have to write this because we already had it here. And so we could have done the ratio test without having to write this. I have red, I have black, so let's get some blue going. So the ratio test says, no. Okay, the ratio test says lim, right, as n goes to infinity, and then, what is it? The absolute value of an plus 1 over an. And if this is to converge, we need to say that this, an absolute value, is less than 1. We're not trying to figure out if this converges. We're trying to make it converge. We're trying to figure out the interval of convergence. So this is already decided, right? And so what does this look like in this case? Well, we see that this is a sub n, which is the same as this, right? And so then when we do a sub n plus 1 over a sub n, I need the space, so let me put that there, and I can make it smaller, so there it is. Okay, so when we do this part, what we have to write then is this, right? So we go lim, and then as n goes to infinity, and then it's going to be absolute value. Let's not forget our absolute value. A sub n plus 1 has got to be longer, right? Okay. Can I use a ruler? I'm really a neat freak. And maybe just generally a freak. Definitely a neat freak, though. I don't know about the general freak, but definitely a freak. All right. A neat freak, I meant. Okay. A sub n plus 1 is going to be negative 1 to the n plus 1 plus 1, so n plus 2. And then x to the n plus 1 plus 1, so then n plus 2, and then over 3 to the n plus 1, and then times n plus 1. And we're going to divide this by a sub n, but a sub n is a quotient. That is, it's a fraction, so dividing by a fraction is the same as multiplying by its reciprocal, so we're going to do just that. So 3 to the n times n, and then over negative 1 to the n plus 1, and then x to the n plus 1, and we psycho, it's freaking 2 a.m. and I'm making a math video. This is probably why one of my neighbors hates me. No, he doesn't really hate me. He's you're good, bro, is what he said to me one time when I was oh dude, if I'm really loud when I'm making these math videos, I'm I'll work around your schedule if you want, and he's nah, you're good, bro. But I somehow still kind of don't like him. No, it's not true. My neighbors are really cool people, pretty much all of them, and a couple of them are really old, so it's really hard to fight with old people, right? But life, it's tricky. Getting along with people is kind of difficult, right? Okay, anyway, but when you're talking at a video by yourself, it's pretty hard to fight with anything. Especially at this hour. Why do you think I stay so late? There is no one. Okay, and there is this until I can hide in the woods sometime. Like, this is the second best thing. Hold on, let me circle these in black. I'm having way too much fun. So, this, and then this, and then this, and who else? And then this, and then this are the survivors inside. Okay, well, obviously the -1, because we're going to take the absolute value, we could just ignore it, right? And so then we have x over 3, and let me continue in blue. Sorry, y'all. So x over 3, and remember the absolute value of AB is the absolute value of A times the absolute value of B, and we kind of want to separate the things that have to do with N and the things that don't have to do with N, so I'm going to use the rule that I just stated to close off the absolute value here, because like these two items don't have anything to do with N, and then the only other guys, this guy and this guy, have everything to do with N, right? And so we could write times the absolute value of, and this is usually a good habit to write, although it's not necessary, N over N plus 1. The AP will, it's like extra meticulous. The AP will still give you full marks even if you didn't separate it in this manner, as long as you understand that the limit is N goes to infinity of this is 1, right? Okay, and then, so this is less than 1. As I just said, when we apply the limit, we find that this is 1. So then what we have to write next, didn't mean to make it bigger. It got bigger on its own, though. So I didn't mean to make it that small. All right, we'll live. So as I just said, this is 1, as N goes to infinity, and then we don't have to write this anymore because we just applied it. So what we're going to get is absolute value of x over 3 is less than 1. But then there's the other absolute value rule. Absolute value of A over B is absolute value of A over absolute value of B. So applying that, we see that what we're going to have to write is absolute value of x over 3 is less than 1. Then from here, we multiply both sides by 3. So we're going to get absolute value of x is less than 3. And the translation of this appropriate is this. -3 to free it of the absolute value is less than x is less than 3. Got it. Okay, but are we done? No. It says interval of convergence. Why are we not done? Because we must do the endpoint analysis. On these kinds of questions, if the question is worth 4 points, the endpoint analysis is worth at least 1 point. So basically, I'm saying the endpoint analysis is pretty crucial. Pretty crucial. That's Larry David. Right? Pretty crucial. Okay. So then this here, f of x, right, is going to turn into what at the endpoints? Well, when x is equal to, where should we start? I suppose -3, because that's on the left end. So when x is -3, what we're going to get is, so we are checking this endpoint, and so we're replacing that x with it. So what we're going to get is -1, and then, was it -1 to the n plus 1? My bad, y'all. That didn't affect anything except for what I wrote over here, right? So far, our work was unaffected, but I knew that that was kind of missing because I can kind of like expect what we're supposed to get, which is that we have this, and then I plug in -3 for x, and so we're going to get -3 to the n plus 1. Now, using exponent rules, notice we can write -3 to the n plus 1 is -1 to the n plus 1, and then times 3 to the n plus 1, right? And so it's precisely because of this that I knew that there was a plus 1 missing there, because this is supposed to work out nicer. So now, what is this? Well, you can see it as one of two ways. You can see it as -1 to the 2n plus 2, or you can see it as -1 to the n plus 1 all squared. Either way, if you're, whatever this is, if you're squaring it, it's going to be +1. And if you see it this way, this exponent is always even. -1 to an even exponent is always +1. So no matter what you do, brother. No, I'm talking like an African. No matter what you do, brother, this is going to turn into a +1. You understand? Okay, so then we slide this over. What else is missing from this brother? What's missing? What's missing is this. Sorry. Yes, I laugh at my own jokes. Over 3 to the n, and then times n, right? Okay. Brother. this and this are gonna cancel to a 3. And sigma properties will allow us to write that 3 in front. And then we can get rid of this. And we just have an n in the bottom and then a 1 at the top. All right. This is still a good video, right, guys? Even though I'm laughing. Okay, now this is clearly 3 times a very, very, very famous series in the series world, and that is the harmonic series that I just lassoed. And we know famously the harmonic series diverges. So if you multiply a divergent series by any constant, including 3, it's still going to diverge, meaning this endpoint is not included. So we just learned that -3 is not going to be included in the interval of convergence. All right, so then what about +3? +3 is going to be included, and that's because f of x at +3, you should already see this. I'm going to do this super efficiently, no jokes about the brada. It's going to turn into -1 to the n plus 1, and then isn't it 3 to the n plus 1? So that's 3 to the n, right? I'll write the 3 to the n here, and then the 3 out here, and then divided by 3 to the n times n, right? Okay, so this cancels, and now we have 3 times the alternating harmonic. What I'm saying is f of x is equal to 3 times, and this extra writing really isn't required. I just want you to see clearly now. The rain is gone. I swear, I'm only on Jesus. I'm not on anything. Like, trust Jesus, love him, and like, follow him, and you will laugh even more than I do. It's not that I'm always this happy, like, I'm not, but I'm, like, through Jesus, like, a pretty happy man. Thank you, Jesus. Okay, so this here is the alternating harmonic, and so 3 times the alternating harmonic is going to converge because the alternating harmonic famously converges. Okay, now notice that this last question, as I said, like as tradition, is going to be about the alternating series truncation error, or the alternating series error bound, as they've called it. Those are the 2 names for it. And as I said, that this year they have tossed this out. Now, because as you can see, part B was so time consuming, this question only had 3 parts, whereas the last question, which also had the alternating series error bound, had 4 parts. But who cares? I don't need to do that because it's not going to be on the test, right? And you want me to focus on what's on the test, don't you? Don't you? Huh? Okay, that's what I thought. All right, so here it goes. So what is next? Next is, Jesus, are we really going to keep going? Okay, you're not tailored out. Okay, so let's see. So this is what? A function f has derivatives of all orders. The derivative of f satisfies the maclaurin series, blah, blah, blah. Show that the first 3 non-zero terms. Okay, guys, I'm not going to do this. Should I? Like, okay, and then the general term. Determine whether or not the maclaurin series described converges absolutely, converges conditionally. Yeah, okay, let's do it because part B is a little different. But otherwise, we know for the first 4 non-zero terms, we know that they're supposed to be, like, let's write the general form. Okay, at this point, you should have this, like, etched in your memory if you haven't already. Jesus, who is that? No, it's just, like, people working hard like me, right? Like, all over the night. X squared, and then plus, and then it's f triple prime of 0 x cubed over 3 factorial, right? Okay, that's the first 3 non-zero terms, right? Oh, 4. Okay, these are 4. 1, 2, 3, 4. I don't know how to count. Okay, so f of 0 is 0. Oh, thank you. F of 0 is 0, so we have to actually write one more. So the 4th derivative evaluated at 0, and then x to the 4th over 4 factorial, right? Maybe we have to write more than that. There's like a pest in here, like, it's like not a fly, not a bee. I know what they look like. I just had to, like, catch it real quick. I think I did. Anyway, this here is 0. So f prime of 0 is 1. So next is going to be plus x, right? f double prime of 0. For n greater than 1, this is how the derivatives are defined. So since we know that all we need are the derivatives, let's get on with them, right? So like, let's see. So for 2, we're going to have to pick n to be 1, right? Note 1 is included in that. So we're going to have to write f 1 plus 1, and that's of 0. So that's going to say by the right-hand side. Negative n is 1 in this case, specifically that 1 right there in case you're not seeing. So negative, and then 1 times, and then f prime of 0, right? Yeah. This is 1, meaning f prime, right? Okay, so we've been through that. So f prime of 0, they said is 1. So this is going to be, in total, this is going to be negative 1 times 1, which is negative 1, right? Okay, again, because f prime of 0 by the given is 1. Okay, well, this is given also as a formula, though. Anyway, f 2 plus 1 of 0 is going to be negative 2 times, and so this is f triple prime, right? So f triple prime of 0, this clearly is f double prime, right, of 0. Okay, oh, I fit that in, nice. So it's going to be negative 2, and then f prime of, and then f prime of what? No, f, what is n this time? It's 2, right? Yeah, that's right there. So f double prime of 0. It better be, because otherwise, yeah, it wouldn't have made sense anyway. So it's negative 2 times negative 1, which is positive 2. Got it. And yeah, determine whether the maclaurin series described converges absolutely conditionally. Okay. Can we answer B without finishing this? Because, this is trivial. Like, because basically, like, when we substitute in here, I already got you started. It's 0 plus x, and so we get x, and then plus f double prime. We just calculated is negative 1, so it's really actually x minus, and then 1, right? And then we're working on this right now, right? Yeah, and that's over 2 factorial, and then times x squared. And the next one we've already gotten, it's 2, right? So plus 2 over 3 factorial x cubed. So if we've matched so far, then I'm satisfied. I don't know if you are that. And then what happened to this? Yeah, okay, because like this is 6. 2 over 6 is a third. So all right, guys, like I'm not gonna do this anymore. And that's because we can answer B without like checking that, like, let's like be reasonable on your time and my time, right? Okay, cool. So determine whether the maclaurin series describe converges absolutely conditionally. Fine. So it's about convergence, right? So we need to first write in closed form. So in closed form, what do we write? Well, it's going to be what are these guys looking like? So we could write this as over 1 to the first, right? So we can go n equals 1 to infinity. Although it's only 4 terms, I just want to write in general. And then it's going to be what? Negative 1, because they're alternating. Negative 1 to the what? Well, when n equals 1, I want a positive. So negative 1 to the n plus 1 then, if I start at n equals 1. And then, what is it? Otherwise, it's going to be x to the n over n, right? That's what it looks like. Okay, fine. So when to see if this converges absolutely or conditionally, what we're going to have to do is like for x equals 1, well, when x equals 1, this is going to turn into this. This is why, like, when I teach this topic, Taylor and maclaurin series, actually series convergence, when I teach that, I abusively like talk about the harmonic and alternating harmonic, because they come up so frequently. Because when x is equal to 1, we get 1 to the n, which is just 1 over n. And so then when we look at this in absolute value, what we're going to get is this here, n equals 1 to infinity, and then 1 over n, which is the famous harmonic series. It diverges. So this series does not, when x is equal to 1, it does not converge an absolute value, and therefore it doesn't converge absolutely. But without the absolute values, it does converge, because it's the alternating harmonic when we get rid of that. And so then we say that this converges conditionally, because, well, it doesn't converge an absolute value, but it converges conditionally. Okay, C is, right, the first 4 non-zero terms and the general term of the maclaurin series for g of x. Okay, guys, we've done a series that we found by integrating in a previous problem, so I'm not going to do part C. Let's keep it moving, because as I said, there are interesting questions that are to come, and those are going to expose you to a different variety than what we've seen so far, and so we better get to those, and that'll be like kind of better, like a lot better, right? Jesus Christ, this pest needs to go away. It's like this girl I was in love with, like a pest. No, I'm kidding. Like, am I still in love? No. Okay. So, 6. Here I go, thinking of you again. No, I'm kidding. I'm only in love with Jesus. And that's for real. No jokes about that. Seeing how many times I shout out his name, like, should be enough evidence. 6. The function f has a Taylor series. I'm spinning my pen if you can hear that. X equals 1 converges to f of x. And it is known that blah, blah, blah. The nth derivative of f, yeah, so same old game they're playing, right? The first 4 non-zero terms and the general term, no. Like, we're not doing that because this is very straightforward. You've got, like, the start, right? You've got f of 1. The only thing different is it's not centered at 0 this time. It's f of 1 plus f prime of 1. And then otherwise, the same old x, and then over 1 factorial. But who cares about that? F double prime of 1, x squared, and then over 2 factorial, and plus f triple prime of 1 over 3 factorial, and then x cubed. And so they said, what, the first 4 non-zero terms? That should be the first 4 non-zero terms, and knock yourself out. You do that. I'm not going to do that. But I know why I picked this question is because, like, B is quite different, right? It says the Taylor series for f of x has a radius of convergence of 2. I see. So, and it's centered at 1. So what that means, and this is like, you don't have to do the ratio test anymore. You need to find the interval of convergence. Remember, interval of convergence is always like automatic ratio test, right? There are 2 exceptions. One is a situation like this where you're given the radius and the center, right? The center is what this Taylor series is centered about, which is that x equals 1. And we also know the radius here, right? When you know that, then you don't have to do the ratio test, because if it's centered at x equals 1 and it has a radius of convergence of 2, then you go 2 to the right of 1, that lands you at 3, and 2 to the left of 1, that lands you at -1, right? And so this is one of the exceptions to doing the ratio test for an interval of convergence question. The other exception is if the series is an infinite geometric, right? Because if it's an infinite geometric, then we know the interval of convergence is the absolute value of r, the common ratio being less than 1, right? Which is -1 is less than r is less than 1. So this and a situation like this is when you could avoid the ratio test. So it says, find the interval of convergence. Okay, unfortunately, though, we still have to do the endpoint analysis. So right now, what we've discovered is -1 is less than, x is less than 3. But we need to do the endpoint analysis for -1 and 3. Okay, I will be shocked and surprised if this is not about the harmonic and alternating harmonic. Watch it invariably be about them when we plug in the endpoints, that is. But first, of course, we need the general form of f of x. And don't worry, we're not going to pay for not having done like part A because, well, we're at a party. Part A. I had like a department chair when I was really young, and a teacher at a private school who like really liked the idea that part A and part T, party, as in like a party, like really sound like one another. So she always cracked that joke, part A, party. Okay, I'm like, all right. I mean, I'm too grown for this now. Old as heck, but -1 to the n, but still have the spirit of a young man. And over 2 to the n here, right? Okay, so we have the fn, right? The fn of 1, and that's required, right? Because, like, remember the Taylor is like, in general, the Taylor series, right? I already wrote it, you should know. If it's fn of a over n factorial, and then x minus a to the n. So we're, part way there. This here represents, sorry guys, I didn't want to, I stopped myself because I realized I was going to circle too much. It's fn of a is what that is. They even said, right? Like for 1, right? Okay, so we've got that part. So we've got a little bit of our work cut out for us, but we still need to write more to say what f of x is here in general, right? Like, so, but I needed space. Okay, so then what else do we need? We need clearly x minus a to the n in this part, and a is 1, so x minus 1 to the n. And then, of course, we need to divide fn of a, fn of 1, by n factorial, which amounts to throwing an n factorial with the 2 to the n in the denominator right here, right? Okay, cool. So let us do that. So we go n factorial right here, yeah? Okay, cool. Now, where to from here? Jesus Christ, someone likes riding motorcycles at 3 a.m. in the morning. Okay, let's make this small, right? Because we only need it for reference. All right, so the endpoints, that's why we did all this. So when x is equal to -1, right? When x is equal to -1, that means we replace this with a -1. Notice that means that we have -1 minus 1, which is -2 to the n, right? Okay, so then the series, when x is equal to -1 at the left endpoint, the series is going to turn into f of x is equal to, and yeah, there's an infinity right here, but we'll live. The series is going to turn into n equals 0 to infinity, and then it's -1 to the n, and then what is it? -1 minus 1 is oh well, we have this part, sorry guys, which is n minus 1 factorial. Whoa, wait. We know n minus 1 factorial over n factorial, you can tell that I don't do these problems ahead of time, is equal to 1 over n, right? Because n factorial is n times n minus 1 factorial. So then we could just do that. Okay. So like, let's get rid of this. And let's write, in place of n factorial right there, let's just write an n, right? So we have a 1 here and then an n there. Okay. And as I said, otherwise, we're going to have now over 2 to the n. Surprise, surprise, it's going to turn into the harmonic, right? Or alternating harmonic, one of the two, as I said. When x is equal to -1, as I said, we're going to have -2 to the n. Make a habit of writing things like this as -1 to the n, and then, well, the number otherwise to the n. Now, this and this are going to combine to +1 for reasons you should know. It's going to be -1 to the 2n. That's always an even exponent. And this are going to cancel. Surprise, surprise. So we have the harmonic series, and so then we have 1 over n. So this is the harmonic series, and we know it, do I have to say it? It diverges. So then we don't have to include this endpoint. That's the point. Okay, so when okay, do we have to even do it? Alternating harmonic, right? Like, let's take a wild guess. And I guess I'm saying that on this AP, if you're confused about a question like this, just write alternating harmonic and harmonic, like if you don't know what you're doing. So -1 to the n, and so this time it's for 3, right? Clearly 3 minus 1 is 2. So -1 to the n, and then 2 to the n. From what I just said, this part's going to turn into 2 to the n. Otherwise, over 2 to the n, and then n. These cancel, which means that we have the alternating harmonic, because that just 1 over n. The alternating harmonic famously converges, so it means that we have to include this. Yeah? Okay, cool. So what's next? Oh, yes, we're almost at the end. I didn't know. See, time flies when you're having fun. I didn't know that I was already at the 2016, but that's great. So part C, what does it say? The Taylor series can be used to represent f of 1.2 as an alternate. Use the first 3 non-zero terms. Okay, you already would have figured out the first 3 non-zero terms based on this, right? Like, and the derivatives are given by this, and then the first 2, these guys, are given by these 2, right? So you do that and just plug a 1.2. That's all there is to that. So I'm not going to do that because it's really silly and simple. All right. So to conclude, this is a problem that I got from like this really awesome African American student. Like, really didn't need to say her background, but like I don't know, like I'm like part black, but mostly German. But anyway, I wanted to share because like I'm always appreciative of like when stereotypes are defied. She's like super smart, and I mean, we know that like math is the great equalizer, meaning that like language, right? Like if your parents are like from a certain background, then the way they speak at home and all that, like that could influence like who you are, and therefore like give you a leg up. But math is like the great equalizer, is what this like really old teacher who taught at that private school that I mentioned, he taught there for 35 years. And this is when I knew I need to stop being a teacher in the classroom, is because like one time I smelled alcohol in his breath, and this guy's like an amazing teacher, like one of the best I've ever come across, and his students loved him and all that. But like teaching is like when you do it for that long, you can only become an alcoholic. I call it a young Asian, amazing girl, like a teacher who was my colleague at one job one time told me like, what are you gonna do long term? And when I spoke that I'll be a classroom teacher, like, because I love it, she's like, well, don't all teachers just turn out to be alcoholics? So I found out through him that like, okay, maybe I should like do something else. um, but anyway, he famously told me that like math is the great equalizer, because he'd see all these like scholarship like admits who to the private school, like black kids and Hispanic kids that are at the school because of scholarships, and they do as well as the white kids on the math, because, well, again, like for math, language is not a barrier. You either like understand like numbers and shit. I mean, sorry about my language, or you don't. Anyway, so like on that part, like we're all equal. Math is a fair game, is what I'm saying. Anyway, read this. So let f be a function having derivatives of all orders for all real numbers. The third degree Taylor polynomial for f about x equal to is given. So there that is. Find f of 2 and f double prime of 2. That's what it says, right? Okay, well, we know by the definition of the Taylor series that it's going to have to be, since it's centered at 2, it's f of 2 plus f prime of 2 plus, f prime of 2 times x minus 2. I'm rushing because I'm eager to finish, over, 1 factorial, but I don't need to write that part, right? So plus f double prime of 2 over 2 factorial, and then x minus 2 to the second, and then yada yada, right? But let's write it anyways. One more. F triple prime of 2 over 3 factorial. We've seen this like over and over, so maybe right now you're thanking me for skipping some of the repetitive ones. Anyway, so based on this and comparing that to this, we can clearly see that f of 2 has to be the first term, right? And so that's 7. So f of 2 is 7. As you can see, this is posed differently. And then f double prime of 2 has to be f double prime of 2 over 2 factorial has to be this here. So f double prime of 2 over 2 factorial has to equal minus 9, meaning f double prime of 2 is equal to minus 9 times 2 factorial, which is minus 18, right? Okay, so that's how you answer part A. Part B. Is there enough information given to determine whether f has a critical number point at x equals 2? What are critical points? Critical points are where f prime is equal to 0 or undefined. F prime undefined, right? Remember, it's not just where f prime is equal to 0. That almost every kid knows is a critical number, but y'all forget that f prime undefined also gives rise to critical numbers. Well, we can clearly see that in this T of x Taylor expansion, there is no x minus 2 term, which means that f prime of 2 had to have been 0 in order for it to drop, right? So the answer is yes, there is enough information because the x minus 2 term is missing. Okay, so cool. And it says, if so, determine whether f of 2 is a relative minimum. Well, okay, fine. For that, remember, usually what we do is we draw a number line and then we put the critical number 2 on there, right? And then we test, this is a number line for f prime, we test numbers into f prime to the left and to the right of 2, and if it goes from positive to negative, we say it has a local max, and if it's from negative to positive, we say it has a local min. Now, you can attempt to approximate f prime by finding t prime, but instead we can use a second derivative test, because remember, the second derivative test said if you have a horizontal tangent and you're concave up, you're a local min. The horizontal tangent, meaning f prime is 0, we already established that is true at x equals 2, but if you have a horizontal tangent and you're concave down at that x, then you're a local max. Fine. So all we have to do is look at f double prime of 2. Oh wait, surprise, surprise, we already figured out that that's negative 18. So f double prime of 2 is less than 0, meaning that our function is concave down at x equals 2, and it has a horizontal tangent there, meaning we have a relative maximum right there. Okay, so this brings us to the conclusion, and because like I would have to guess what topic the second question has to be, and again, I bet you everything I've got that Taylor and Maclaurin series will be one of the questions on this year's one of the two questions on this year's FRQ for BC. But the other question is hard to predict what topic they're gonna pick. And so like I can't just make a video about every topic. That's why I chose this, and so this will be the only AP prep video I will have. As I said, I have previously made full FRQ solutions. I'll point you to where those are, and so you can watch those videos if you want to look through the diversity of questions and all the possibilities of what that second question can be. And yes, when I say what that second question will be or can be, it's as if I already know that this will be on there. Yes, I do. Come and thank me later. You will have been very happy that you watched this video. Come May 5th when you sit to take this FRQ test, right? Okay, otherwise, stay safe, pray to Jesus. Hope you're well and your families are well, and take care. Keep watching.